All right, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Friday, January the 31st, the last day of January. We're cruising through this already. We're already finished in January. It's going to be end of school soon enough, so we need to get the proverbial rear in gear. So today we're going to be talking about how to calculate empirical formulas and molecular formulas from percent composition. But before I do that, if you are enjoying these exciting episodes, be sure to hit that like button and ring that notification bell and subscribe to my channel. And you have all the chemistry you could ever want right there at your fingertips. Or a sleep aid if you have trouble sleeping at night.
Oh yeah.
All right, here we go. We were working yesterday on determining the empirical formula for percent composition data. We're working on this number 36, and you might want to put this on there. This is on page 248 in your book is where this is coming from. It's actually in the next chapter, but we're going to just kind of do this as this independent unit and then come back and look at the rest of chapter 7. Okay? So we had 3 steps. And I still have step 1 on the board. Step 1, it says to do what? Anyone? Assume 100 grams. Why? That doesn't matter how much we have. Will this percentage change based upon however much I have? Will this percentage change if I have 5 grams, 10 grams, or a bazillion grams? No. The law of definite composition says no matter what, it's always the same percent composition by mass. Compounds have a definite composition. That's the law of definite composition. All right, so let's make the math easy. We assume 100 grams, therefore you can change percent directly to grams. Now, we got farther in first period than I did in 7th period where this is from. What was the second step? Convert grams of each substance to moles using what? The molar mass of each substance. And where do we get that molar mass? On the periodic table. Okay, so we've been doing that. We already know we've been doing that since chapter, when we did conversion factors, we did grams to moles in chapter 3. Okay, so we're just going to use the periodic table, set it up. So we went through and we did this, and we said, you already have this in your notes, times 1 mole over the 107.9 grams times 1 mole over the 14.01 grams and times 1 mole over the 16.00 grams. Again, this is the number that's coming from the periodic table. This is the atomic mass, right? You should already, we did this yesterday, so you should already have it. So somebody read out the numbers that we got here. Was this 0.5587? 0.5587 moles of silver. This turned out to be 0.559 something. 5593. The other class somehow got 89 over here instead of 93, but it doesn't really matter. It's not going to affect anything. And the last number is 1.766 moles of oxygen. Okay? So now we have a mole ratio because our empirical formula is not a gram ratio. We don't have, and when I say the formula, and we know the formula is going to be AgNO3, that doesn't mean 1 gram of silver to 1 gram of nitrogen to 3 grams of oxygen. It means 1 mole of silver to 1 mole of nitrogen to 3 moles of oxygen. Remember, moles is an amount. It's just like, it's just a big pile of molecules. And so we need a mole ratio. So I have a mole ratio here, but you're never going to see a formula Ag 0.55, N 0.55, O 1.7, whatever. It's always going to be whole numbers. So if this is indeed a compound, which it is, these should be in a whole number ratio. So how did we determine that whole number ratio? It's divided by the smallest number. So number 3, I never really wrote it down, is divide each mole value by the smallest mole value. And what does that give you? Why do we want to do that? What do you get? You get a whole number ratio. So I'm out of space here, but write in your notes, divide each mole value by the smallest mole value to get a whole number ratio. To get a whole number ratio. So we went through this. What's the smallest mole value here? 0.5887. So we divide this by 0.5587 divided by 0.5587 divided by 0.5587. This turns out to be 1. This turns out to be 1. That turned out to be 2.99, which is 3. Okay? So now I have my mole ratio, so my empirical formula then of this compound is going to be what? Ag1N1O3. AgNO3. Okay? Now is this going to be an ionic, metallic, covalent network, or covalent molecular compound? How do we know? It's very simple. It's got a metal and an ion, metal and nonmetals. So it's going to be ionic. You look at the first thing, it's ionic. It's not hard. It's either a metal or it's a nonmetal. It's either ionic or it's covalent. We got to get in your head. Okay? How do we know if it's covalent network? It's one of the 5, which this isn't. And how do I know if it's just metallic? It's just copper, it's just gold, it's just magnesium, it's just one metal. Okay? So really, if it's a compound, it's either going to be ionic or covalent. Again, how do we tell it's ionic? How do you tell it's ionic? A metal. You look at the very first thing, it's a metal and a nonmetal. Okay? How do I know it's covalent? 2 nonmetals. So again, the second thing's always nonmetal, so you just look at the first thing. If it's a metal, it's ionic. If it's a nonmetal, it's covalent. Ionic compounds do not form molecules. So we always express them just in terms of our empirical formula. Okay? We don't ever have to go any farther than this, or further than this. It's a concept. Would I go further or would I go farther? We don't need to go any further than this. Okay? And so because it's an ionic compound, ionic compounds are always described by it's just the simplest ratio, empirical formula. All right? So let's look at another one then. Let's look at number 37. We're going to follow the exact same 3 steps. So what do? We get a new marker first. So it's the first thing I do. So I can just say I have 52.11 grams of carbon. How much? What's the next one? 13.14 grams of hydrogen and 34.75 grams of oxygen. Right? Step 2. Convert grams to moles. So how am I going to do that? Somebody tell me. Okay? So I'm going to go here I'm going to use the molar mass of a carbon, which we all know to be. Now that's oxygen. 12.01. And where does grams need to go? Because grams on the top, I'm going to divide. So I'm going to say 1 mole over 12.01 grams. Okay, what am I going to do for hydrogen? What do we know hydrogen's molar mass is, the atomic mass? 1.01, O is a letter. 1.01, 1 mole. And by the way, if I ever say that, you're allowed to correct me. 1.01, I'm on a mission from God. I've been on a mission for 40 years. I still haven't completed the mission. But O is a letter, 0 is a number. Let's not discriminate against 0. Okay? And then lastly, oxygen's is going to be 1 mole over 16.00 grams. So someone on a calculator, let's just get some values here. Okay? You need to be writing this down.
The first one is 4.339.
9?
Well, I just rounded it.
That's fine, that's what is perfect, it's 4 sig figs. Moles of carbon. And I highly recommend you use your units. Units are your friend, they let keep track of what the number is. Okay?
What?
What's the second one? Anyone? 13.01.
13.01. You're rounding to 3. You're rounding 4 seconds.
And the last one?
339.
Anyone got the last one for me? Two point one.
Wait, hold on.
Oh, no, no. Yeah, you're right.
I have 2.35.
2.35. Somebody else agree with that?
2.1.
Oh, I did the wrong number.
2.17.
Yes.
172. Are we agreeing with that number? Two or more agree. There we go. So now again, so I've converted to moles. Okay, your empirical formula is never a gram ratio, it's a mole ratio. So you convert to moles, but now once you have it in moles, I need a whole number ratio. So this is, if this is a compound, true compound, these should be in some whole number ratio. So, what do? Divide by the smallest one. Okay, so because if this is the smallest one, these should all be some kind of multiple of that smallest one. So we divide by 2.17. Steve, I'm having issues, it's Friday. 2.172, 2.172, 2.172. Obviously this is 1. I would guess that this is going to come out pretty close to 2. What did it come out to exactly? Anybody divide it?
1.99.
Would say it again?
1.99.
1.99. Okay, that's pretty close enough for government word for 2 to me. Okay, and what about the hydrogen?
6.
6. Did it come out to exactly 6?
5.9898.
5.998 again. All right, so that's all close enough. Okay, because it's going to be important that it's close. When you divide through, it needs to be within kind of 0.05, 0.06, pretty close to a whole number where you can round it off. Every once in a blue moon, and we're going to do one next, every once in a blue moon, it comes out to like 2.5 instead of 2. Well, that's too far away. Well, I'm going to show you how to deal with that next. And then that's the last thing we're going to talk about. Okay, so what would my empirical formula be though on this? C2H6O. Which, more than likely, we would rewrite, or we could do the Lewis dot structure to make it look like this. C2H6O. But it's going to look like this. Anybody recognize what that is? We just did it in one of our activities and all that. Anybody remember what the prefix for 2 carbons was? No. Remember the organic compounds. We just did that. Think of the evaporation lab you just turned in. This is one of the ones you just did on the evaporation lab. If they have an OH, what do they all end in? All OL, okay? And remember that meth is equal to 1, F was equal to 2, Pro is equal to 3, and But, not but, But is 4. So this was the ethanol. We used methanol, ethanol, propanol, and butanol. Those were the 4 things that we watched evaporate. Okay? So, that's a little on my information here. Okay, so we have this. All right, let's look at one more. I'm gonna make one up. All right. Seventeen times, 16 times 7, 112.
Let me check, Yep.
Okay. So, 78.2.
What is that? My perfect average. You just missed. Yeah, I know.
26.58%. 26.58% potassium. 1112. 38.1% chromium, and then 112 divided by 38.1. Oh, that's not what I want. Sorry, this number's not right. It's 38.1% oxygen, and then 104. 35.4%. So we'll just go 20 times 26.6. So what does that all add up to? 10, 11, carry my 1, 7, 12, 20. Okay, so it's because I'm rounding that these aren't exact. So if we go 5, let's go 5, 8. Let's go 35.35 and 38.07. That'll give us more accurate. All right, let's see what. Let's go through steps 1, 2, and 3 here. So you guys go through steps 1, 2, and 3 and see what you get. Then what do we do? By molar mass. So it's 1 mole over 39.10, okay? Times 1 mole over, it's 51.99 something. I did 52.00. Does it come out to pretty much that? Okay, and then this one is always 16. Hopefully we're getting to know that one without having to look it up. Okay, so what does this one come out to? 0.6798 moles of potassium. This one came out to the exact same thing, didn't it?
Yes.
So what do you think that means about those two?
Close on the periodic table.
No, not necessarily close on the periodic table. The ratio is going to be the same in the compound, whatever it is. If it was, it's going to turn out to be 1-to-1, but well, actually not really. But it's going to be the same as for whatever they are. Okay, so whatever subscript is on potassium, the same subscript is going to be on chromium. And then the last one comes out to 2.17.
170. Or no, sorry, 379.
379.
I was looking at the wrong one.
Okay? Now look, the next step is to divide by the smallest one. Do we need to physically write it out here? Can you see that this is the smallest one? Okay? I mean, you don't have to actually divide it out. Please don't put 0.6798 divided by 6.6798 into your calculator. Please. Okay? We know you can see. So I just know that this is 1, this is 1. This is the only one I'm actually going to divide out. Okay? You can just know that, okay? Everybody can see that. When you divide this by this, it's going to be 1. So this turns out, what does it turn out to? 3.5. Now y'all, that is not close enough to round to 3 or 4. That's going to be right in the middle. You need to be, again, this decimal needs to be 3.05, 2.95. Then you can round it off to a 3 or a 4. Okay? But if it's 3.33, 3.5, 3.66, it's going to come out to some common fraction. What common fraction is 0.5? 1/2, right? So I need to get this to a whole number, keep the ratio. This is a 1-to-1 to 3.5. What's the whole number ratio going to be? What is this all going to be in a whole number ratio? If this is 1-to-1 to 3.5, the whole number ratio is going to be, come on,
2 to 2 to 7.
say that again.
2 to 2 to 7.
2 to 2 to 7. We just have to multiply whatever this fraction is here. Since that's 1/2, we're going to multiply by 2. So my ratio is going to be 2 to 2 to 7. Not every empirical formula is going to have a 1 in it as a subscript. So the formula of this compound is going to be K2Cr2O7. It's a 2 to 2 to 7. That's still the empirical formula. That's still the simplest ratio. Okay? Now, so if this happened to be 3.33, what do you think we would have to multiply it by? 3. Now again, it may come out, experimental data, it may come out to 3.32, 3.34. But still, if you multiply it by 3, it's still going to come out to a whole number within that 0.05 range. Okay? So it might come out to 3.65, 3.68. But that you got to know your common fractions. 0.25 is a quarter, 0.33 is a third, 0.5 is a half, 0.666 or 0.67 is 2/3, and 0.75 is 3/4. Whatever the denominator is in the fraction, that's what you multiply it by to get to a whole number. Okay? So if it's a third, you multiply by 3. But if you multiply this by 3, just like in algebra, keep everything the same, multiply this by 3, you got to multiply them all by 3 to keep the ratio. But you got to get a whole number. Most of the time, first go around, you get that whole number. Every once in a while, there are compounds that don't have a 1, and you'll have to multiply it. And with that, we'll do those on Monday in practice. Okay? But we gotta keep going. I gotta just tell you one more thing. Covalent ionic compounds only have empirical formulas, simplest ratio. But covalent compounds have molecular formulas because they form actual molecules. We talked about glucose yesterday, C6H12O6. Is that an empirical formula? Is that the simplest ratio? No, C6H12O6 can get reduced, right? To CH2O. This method only finds the simplest ratio. But sometimes to go to the molecular formula, then we need one more bit of information, is the molecular mass, the mass of the actual molecule. And so when we look at a problem like this, what is the molecular formula of the molecule that has an empirical formula of CH2O? But it has a mass of 120, so the molecular mass is 120. Well, it's always going to be some multiple of the empirical formula. You're never going to have parts of atoms or whatever. So the molecular formula is always going to be a multiple of the empirical formula. So the way that we're going to do this, the next 3 steps, and I don't have time to do it, I'll have to give it to you on Monday, but you just find the empirical formula mass. Now you guys, we're getting better at this, so let's just do this in our head right now, and I'll come back and do it again on Monday, but let's just finish the thought. Carbon's molar mass is what? What's the atomic mass of carbon? 12. Let's just say 12. Let's go whole numbers just for now. 12. What's hydrogen's? 1. So that's 12 plus 2 is 14. And then oxygen's is 16. So that's going to all add up to 30. 12 plus 2 is 14 plus 16 is 30. Right? So this is the empirical formula mass is 30. But it says that the molecular mass is 120. So how many times bigger is the molecular mass than the empirical formula mass? 4. 120 divided by 30 equals 4. Which means that the molecular formula is 4 times the empirical formula. So what do you think that the molecular formula is going to be? C4H8O4. So we have 3 more simple steps that are harder to write down than they are to actually do. Step 4, to get the molecular formula, calculate the empirical formula mass, the mass of the empirical formula. Step 5, divide it into the given molecular mass. It gets a whole number. It's always going to be a whole number. It's never going to be a 3.5 or anything. And then you just multiply the empirical formula by that. Okay? So we're going to practice those on Monday. Lab is going to be on Tuesday. Okay? All right. Y'all have a wonderful weekend and go Jags.